Right, so as discussed previously, in order to deal with the aberration that is caused by the spherical lens, we would design a pre-focusing unit lens, which basically will allow the usage of a spherical lens as a f theta lens. Well, not exactly f theta lens, but it would at least the beam waves that it will produce, the final beam waves on the working space, it would be similar to that of f theta lens. So how it works is as follow. So in pre-focusing unit, we have two lenses. One of them is a moving lens, and other one is a fixed lens. So the the first lens is the one that is negative and collimates the beam, whereas the second one is a focusing lens or the positive lens, which basically converges the beam to the galvanomirrors X and Y. The distance between these two lenses can be changed by moving this particular negative lens, and based on where we want to deflect the or point the beam on the working space, we can readjust the distance between these two lenses in order to obtain a particular beam base size. So as you can see here, this is the representation of how pre-focusing lens works. The collimated beam enter into the moving lens, which is then expanded by the negative lens, and then the focusing lens converges it into the in the two galvanomirrors, which basically then decides where the beam would be reflected. And this is the effective working space, which is due to the factor of cos theta. And this plane working space is what we essentially need. So these are the relations that can be used to decide how much distance do we need to keep between the two lenses. This d naught is the distance between the moving lens and the focusing lens, whereas the d1 is the distance between the focusing lens or the positive lens and the final spot in the working space. So all of these factors are already known. We know the focal length of the lenses of both the lenses. We know the m square factor, which is essentially the magnification given by the ratio of the beam waist, initial beam waist and the final beam waist. And we also know the Rayleigh's range, and that's pretty much it. So using these relations, we then plot we obtain the following um, the following flat working space for the pre-deflection unit. And as you can clearly see that if we change the deflection between the odd angle of incidence between -15 to +15 degrees, the working space essentially remains flat, as you can see here. And also, in order to compare it with the previous one, as for the with the spherical lens, we again plot the contour for the final spot size, and it can be clearly seen that for the after the first lens, the change in spot size is almost negligible, which stays same in the center as well as towards the corner to about 3.5 micrometer. And from the second lens to the final spot on the working space, it also remains same to around about 20.1 micrometer. If you compare it with the previous plot that we had for the spherical lens, you can clearly see that if we move towards the edge, the spot size changed to about 21.4 micrometer, which is a huge difference compared to 20.8. But here you can see the change is not that huge, and the spot size in the center as well as towards the corner stays to about 20.1 micrometer, which is essentially the diameter of the spot size. So it can be observed that the spherical lens, the aberration that is caused by the spherical lens can be corrected by the pre-focusing lens unit. This is the MATLAB code. Let me show you the MATLAB code right here. So essentially, this is the one that I showed you, and this code right here is the design of the pre-focusing lens, where the focal length for both the lenses are already given. We then calculate the beam diameter, the initial spot size, the Rayleigh's range, the final spot size of both the lenses, and the magnification. And then this particular region right here is the working space, the plot on the working space, and these two are the relation that I showed you for the pre-deflection unit, where d naught is the distance between the two lenses, d1 is the distance between the second lens as the final spot size. And then we do the recalculation based on the changing distance d naught, which are given by these particular relations right here, and the rest of that is the plot. So if we run it, we can observe the same plot that I showed you just about now. So this is the flat working space. This is the spot size after the after second lens. This is the spot size after the first lens, and as you can see that the lens basically the entire system basically works as f theta lens, although it employs a spherical lenses. So aberration is basically corrected when you use the pre-focusing deflection unit. Right. For the last part of this analysis, we have the design optimization of f theta lens for the three lenses using a ZMax software. So this is already a case study done in one of the papers, and we have simply employed the already available lenses, their thickness as well as their distance between them with the given materials, and we simply simulate their behavior in the MATLAB. So this particular table summarizes all the properties and characteristic of the f theta lens system using three lenses that the authors have designed of this particular paper. I would provide the reference for this paper in the description, or the other resources that I will share. And this is basically the formula or the relation that we employed in order to find the final focal length of the entire system. And if we plot this here in the last part using the Zmax, so you can see that as we move away from the initial center of the working space, the spot size tends to increase massively, and the spot size is basically the minimum in the center. And so this was it for the design of the pre-focusing lens for the scan heads, and this design of the pre-focusing was the most important part of this in order to correct the aberration that is caused by the spherical lenses, and how f theta lenses work, and so on. So that's it for this video, and I will see you in the next.